Welcome everyone to this presentation. In fact, I'm just presenting on the development of the Malawi Active 4 database that has been done by the help of academic institutions. We have Bristol University and Cardiff University within the Prepare Africa project. And the Malawi counterpart, we had the Malawi Polytechnic, Chancellor College, and the MAST, plus the Geological Survey Department of Malawi. Okay. Next slide. Yeah, I think much has already been said regarding the East African Rift System. And as we are aware, most of us here, Malawi is within the western branch of the Rift System and is seismically active. So far, there have been little or no active database for the country for the previous years. Okay. Now, the coming in of Prepare project, I think possibly it was around 2015 when the Geological Survey Department of Malawi went into a joint project with Cardiff University and Bristol. We have managed to develop the Active 4 database. And within the Malawi Rift, Active 4s are defined as those 4s that have been active since the initiation of the East African Rift System. And the AFD is a collection of land features so far stored in their geographic information system so that they are compatible with any GIS software. However, for each feature, we managed to pick on the ground or from the literature is supposed to be associated with attributes, for example, the location, geomorphological aspect of it, geological and seismic information to do with that feature. Okay. Next. So the actual compilation of the Malawi Active 4 database was from the datasets. We used the geological map, and we used the airborne geophysical data, and a high resolution digital elevation model TimeDemX. And the Active 4 database itself complies mostly two shape files. Active, the one is for active faults, and the other one is for inactive faults. And the whole process was modeled to follow the standards of the global earthquake model. And I'm happy to have had a nice presentation from one of the GEM experts. And production of the Malawi Rift Active 4 database used the following datasets. We have already said it. The TimeDemX, it was a 12-meter resolution dataset, and it was very, very useful in the development of the Active 4 database. Okay, next. So this is just the criteria, one of the criteria that was applied when we were developing the Malawi Active 4 database. We had the information from the geological maps. As we can see from the left-hand side, there's a geological map of Malawi. And after referring to the geological map, mainly we are targeting areas where there are some offsetting of the basement and the recent sediments. Then we had to have some field visits to go practical on the field and verify to see if what we noted on the geological map is practically noted in the field. And some of the aspects we used, I've already talked of the TimeDemX, the high resolution digital elevation model, as we can see to the top right-hand side, with very nice triangulated fascias, which indicate activeness of a fault. The integration couldn't go without the inclusion of the geophysical data, which we see in a grayscale down there, and some seismic reflection images from a project that was carried out by Donna Shillington and others. It was called Segment Project. Next. So the strategy, I've already said this, we had the actual tracing, that was the actual digitization of the dam, of the fault from the dam. Then after digitizing, we had to assign the attributes, unique attributes for each and every trace. And fault sections, segments within a fault, for example, we had faults like the Midland Takataka faults that is made up of different segments. So we had to pick each and every segment along the fault zone and give it its own attribute. Then compilation of the fault section. So the table we see, I see an example of the attribute table that we find within the Malawi active fault database. Next. So a significant of the project so far, as a country, we are very happy now to say that we have managed to develop the Malawi active fault database with the help of some academic institutions, Bristol and Cardiff University. And hence we have a platform for sharing information of the active faults within the country. And if incorporated in the seismic hazard assessment of the country, it can give very nice results to see how seismically active the country is. And the MFD provide useful information to planners, for example, to restrict development activities within fault avoidance zones. This is, I think, the end of my presentation. Luke will carry on. There's another presentation coming shortly to be done by Luke. Over to you, Luke. Thank you.
Great, thanks, Hassan. Okay, I'm going to share my presentation. So within Safer Prepare, so what Hassan outlined there is kind of the culmination of work over the past 5 years as part of the Prepare project, and then carried on as the Safer Prepared project in this work package. And the particular challenge of this work package was really to actually incorporate all this new knowledge of the active faults we have in Malawi within probabilistic seismic hazard assessment, and in particular to kind of reduce some of the uncertainties in some of the parameters that we'd estimated in that attribute table that Hassan outlined in order to make it really useful for PSHA. So I should say this is obviously not just my work. You know, Hassan has been you know, a great partner over the past 5 years, and really this wouldn't have been possible without him in particular, but also Patrick Chindandali in Malawi and Felix Mfepo. I've got colleagues from the University of Bristol and also from ARAP. Part of this work was conducted with Grace Campbell and then some institutions in the US as well. And so just to kind of reinforce the importance of mapping the active faults, and I realize there's kind of a wide range of expertise in this webinar. The really key point is that earthquakes occur on active faults. So if we know where the active faults are, we should in theory know where the earthquakes in the future are likely to occur. And we can map these active faults because earthquakes deform the surface of the earth. And so this is a nice example of one of the new faults that we mapped in Malawi. No one previously had known the existence of this. Here's Juliet Biggs, who was the PI of this work package. I think Hassan's in the background of this photo. And it shows a 7-meter high fault scarp caused by 1 or possibly 2 earthquakes over the last few thousand years at the very least. And so we now have this map of active faults for the whole of Malawi. So how do we actually translate that into kind of useful information for probabilistic seismic hazard assessment? So in order to do that, we need to know the slip rate of the faults, how regularly they have earthquakes and how fast they're moving. And traditionally, this would have been done by techniques such as paleoseismology. So you go and look for evidence of past earthquakes in the sediments of these offset faults. We don't have any of that information, unfortunately, for the Malawi rift. So what we did was to divide the extension rate across the rift as a whole, so how quickly the rift is moving apart, and partition that onto faults. And we called this the systems-based approach. There was a paper that came out early this year led by Jack Williams, and really this relied almost completely on the extension rate recorded by GPS. And the most recent estimate of that was this estimate by Saria et al. In 2013 of about 0.9 plus or minus 1.65 millimeters per year. So obviously the uncertainty on this estimate is huge, and that really translates into very, very large uncertainties on our fault slip rates and earthquake recurrence intervals. So for example, earthquake recurrence interval here covers 4 orders of magnitude, so extremely high uncertainty. So what we did was to take new GPS observations. So this again has been work started in Prepare project and continued in Safer Prepare. And really the key part of the Prepare project was to train members of the Malawian Geological Survey Department in GPS deployment and Hassan and Patrick Chindandali were able to continue this GPS survey throughout the COVID pandemic. So a really kind of a great example of the importance of training local geologists and geologists in the skills required to do this seismic hazard assessment. And that relationship has been absolutely key to Safer Prepared for this work package. So these new GPS observations have reduced the uncertainty from 1.6 millimeters per year down to 0.2 millimeters per year uncertainty, and slightly reduced the overall extension rate. So this is now the extension rate across the Malawi Rift. And as part of this this package, these observations, we're actually also able to define a new tectonic plate in Southern Africa called the Sand Plate, which nobody previously knew of its existence. And key to this then has been reducing the uncertainties in our systems-based approach for fault slip rate and earthquake recurrence interval. We're now just down to 2 orders of magnitude, which is still quite large, and is work for the future. And also the fault slip rate uncertainty is massively reduced. One of the aims of this work package in Safer Prepared was actually to go beyond just using geology and to actually measure fault slip rates directly in the field. Unfortunately, COVID kind of prevented this in part, but we were lucky enough to go out to Malawi just before the pandemic in November 2019. Myself, Hassan Mdala, and Grace Campbell from Arup went out and collected data across or collected samples across this fault. This is the Zomba fault in southern Malawi. And what's happened is this fault here, marked in the black lines and the dashed line, has actually offset this sedimentary feature. This is an alluvial fan by around about 30 meters by multiple earthquakes. So what we wanted to do was calculate the age of this alluvial fan feature. And if we know the age and we know the displacement, then we can calculate the slip rate of the fault. So we collected samples. We're still waiting for these samples to be processed. There's been some various delays, but this will be the first fault slip rate in Southern Africa that anyone's ever collected directly using kind of quaternary dating tools, and it will act as a real proof of concept for this method in Southern Africa. During Safer Prepared, we were able to fund a field mission for Hassan Mdala and Felix Mfepo to continue this work. So this work really relies on a lot of field work to identify suitable sites for dating. And Hassan and Felix were able to go out in the faults into the field over the summer this year and to get great constraints on new sites for future fault slip rate measurements. And so I just really want to emphasize that training these local geologists has been key to this approach. And then finally, a really key part of our approach has been open access data. So these active fault databases and an associated seismogenic source database have been archived fully online through Zenodo, but they also have their own GitHub page so that anyone who makes new observations or wants to suggest updates to these databases can do so with the idea that in the long term, Hassan and the Geological Survey Department will kind of control these databases and geologists from Western countries may come in and help them update that, but they're really in control of this data and it's theirs to own and to operate on. So with that, I'll finish, and yeah, I think I'll pass over to Max now for work package 2.